So let's think about the integral of x to the n dx. This calls for an antiderivative of x to the n, also called the indefinite integral of x to the n, but it's an antiderivative is all it is. So the answer is going to be an expression, and I want the derivative, I require the derivative of this expression to be equal to x to the n. Well, we know how we differentiate power functions, which is a term out of a polynomial. And if I was to take the derivative of a power function, we do it by moving the exponent down and then reducing the exponent by 1. So when I take the derivative of this, if I'm going to get x to the n, I would have had to have started with x to the n plus 1. Now again, remember how we take derivatives. If I was to take the derivative of x to the n plus 1, I'd get a coefficient n plus 1, and then x to the power n, reducing that by 1. But I don't want a coefficient of n plus 1. I want to wind up just with the x to the n. So what if I had a constant in here, 1 over n plus 1 times x to the n plus 1? Well, then when I take the derivative, I would get, again, we're hopeful here that that's how that's going to work out, but what do I get when I take this derivative? I get the 1 over n plus 1. Now differentiate x to the n plus 1, so you get an n plus 1, and then differentiate the x term by reducing it by 1, x to the n, and this cancel out, and I'm left with x to the n. And actually we know also, don't we, that the indefinite integral of x to the n, x to the n plus 1 over n plus 1 plus an arbitrary constant c. And we've got just a few seconds left, so let's try one more applied problem here. Let's look at the integral of x to the 5 plus 2 x to the 3 dx. Now, the indefinite integral is a linear operator. So I've got a sum here, and by calling it a linear operator, I'm telling you that you can express the antiderivative of the sum as the sum of the antiderivatives. So this would look like the antiderivative of 2x cubed over here dx, the antiderivative of the first member of this sum plus the antiderivative of the second member. And now let's use what we learned above to take the antiderivative of x to the 5th, and I'm going to say it this way, and I think this makes it so easy. It's x to the, increase the power by 1, to the 6th, divide by the new exponent, 6. Good. Plus, now we've got to take an antiderivative here. So the constant 2 isn't changed by antidifferentiation, so that's just a 2. Now the x cubed becomes an x to the 4, and divide by the new exponent 4, and we owe ourselves a constant c. Now, is that really true? Is that all there is to it? Well, yeah. And how can we prove that? Let's take the derivative. Running a little short on space here. x6 over 6 plus 2x4 over 4, could have reduced that fraction, plus a constant. Take that derivative with respect to x, and what are we going to get? We're going to get 1/6 times 6 x5 plus 2/4 times 4 x3 plus the derivative of the constant is 0. And now we'll do the arithmetic. 1/6, 6, so that's just a 1. So I've got an x to the 5. And it's kind of maybe good that we didn't reduce this fraction here, because you see I've got a 4 in a denominator and I've got a 4 in the numerator, so they're going to cancel out. And I've got a plus 2x cubed, and the derivative of the constant is just 0. So when I take the derivative of 1/6 x to the 6th plus 2/4 x to the 4 plus any constant, I get x to the 5th plus 2x cubed, which is what proves that this expression is the antiderivative of x to the 5th plus 2x cubed. And that's all for now.